weird in a number of ways, but especially in this. They don't actually start to denature proteins, a kid basically under the age of 12, until their fever hits a... I know you miss me. Happens all the time. Watch, this semester it'll get worse. I don't know what Gibbs does to you guys in micro, but there'll be students who are just coming in, and they'll come in and they'll go, they're totally stunned. They don't know where they're at. They just look like, he beats them up in there. I don't know. I don't get it. And as the semester progresses, it'll happen more and more. Just watch. You'll start laughing too, like I do. But anyway, so if the temperature for a child hits 106, then their proteins start to denature. They have some kind of protective mechanism. Nobody knows exactly what it is. They haven't been able to figure this out yet. But they don't start to denature proteins until they get a little higher, which is why, you call the doctor, oh my gosh, my kid has a temperature of 104, and the doctor's like, oh no, you're okay. You're freaking out, but the doctor knows it's not going to be a problem until 106. Now, if it hits 106, that kid's in an ice bath, okay? Because we're causing a lot of problems in the body. The proteins are falling apart. This can cause brain damage, cardiovascular damage, you name it. Lots of damage. Any questions? All right, last part we need to go over before we can take a break and then start lab. Need to just talk a little bit about how enzymes work. Now, enzymes are the globular tertiary proteins, okay? And we said that they were catalysts. That means that they can speed up a chemical reaction. But the other important thing is that it's not totally used up. The enzyme can be recycled. It can be used over and over again. So that's really important. Now, one of the other things in the biological system is that enzymes can also slow down chemical reactions. So for us, they can speed them up and they can slow them down, depending on what you need to happen in the body. All right, so let's talk about how do enzymes do their thing. Give me a second to erase. See? I told you. And this is only the first week. Wait, it'll start happening every day. It's just a good laugh for us, We don't want any micro people in here. And after they've had an exam, they walk in like zombies. Really funny. Okay. So now remember, these enzymes are globs. And they all have a little bit of a different shape to them. But let's just pretend that the enzyme we're going to talk about kind of looks like my two hands together, okay? And so that this enzyme has like a little pocket here and a little pocket here. Now the whole idea of enzymes is they're going to make these reactions go really fast, okay? Whatever they do, they're going to speed reactions up. So let's talk about how slow reactions might go without enzymes. So let's pretend that I build this glass box. All right, I'm going to put this glass box on this table here, and I'm going to tell you there's nothing in the box. There are no molecules, there's no air, there's nothing inside this box. It's my own personal magic box, okay? And what I'm going to do to this box is I'm going to put two separate molecules inside this box exactly 1 centimeter apart. Okay, a little bit less than ½ an inch, 1 centimeter. I'm going to set these two molecules apart. Now my box doesn't vibrate. There's no air to blow these molecules around. All that's going to happen is, remember, molecules, like atoms, have their own internal kinetic vibrating energy, right? And I'm going to place these two molecules 1 centimeter apart, and they're going to vibrate. Now eventually, these two molecules will vibrate enough that they will line up, get close enough together to bond. Now my question for you is, how long would it take, with just the molecule's own internal kinetic energy, for the two of them to find each other when they're only a ½ an inch apart and be able to bond? Give me a guess, Brandon.
I listened.
You listened. Oh, you're so good. You already
10
listened.
years.
It's 10 years. I'm proud somebody listened. They told me you were an A student.
10 years.
That's kudos for you. Did you listen to? I knew it. Because you were smiling when I was cracking my joke about it. Amino acids. Excellent. Kudos for you too. Okay, so it takes 10 years for these two guys to find each other. That's an awful long time for a chemical reaction in our body to actually occur. So here's what enzymes are able to do. The little pockets that I told you about that these enzymes have, they're kind of like big magnets, you might say. They have an attraction for certain chemicals floating around in the cell. And so these little pockets can attract, let's say, chemical A into the first pocket and chemical B into the second pocket. And as soon as these two chemicals enter into this pocket, the enzyme immediately changes shape. And what it does is it slaps those two chemicals together so they can bond, and then it opens up and releases our new molecule. And that all happened in microseconds. So you have something like this. So let's say this is like pocket A, and this is pocket B. And you have certain chemicals floating around out here, C, D, F, H, okay? They're all floating around. Now, pocket A isn't too picky. It'll take any of those chemicals and pull it in. So let's say it pulls F in here. Pocket B, not so much. It's very picky about who it wants in its pocket, and it will only accept C. If an enzyme is super picky about which chemical it's going to let into the pocket, we say this enzyme has a high specificity. So there's only a very specific chemical it's going to let into the pocket. What do you think we would call the enzyme if it's not picky at all? It would let any chemical in. A low specificity, exactly. So specificity means a specific chemical. If it's super picky, it's high. If it's not picky at all, it's a low specificity. And some enzymes aren't picky, some are. So some have a low specificity, some have a high. But once these two molecules come into the pocket and bind, the next thing you're going to see is nothing. They just sit there. Unless you have an important chemical that also binds, and this is our phosphate. Our phosphate is what changes the shape of this enzyme to bring the two chemicals together. So the phosphate causes our enzyme to change shape, and now our two chemicals are able to bond to each other. If you don't have a phosphate around, you can't change the shape of that enzyme. Not going to happen. Now some enzymes, they can't even just do it with a phosphate. They can't just change shape. They also have to have some other chemical that binds, like maybe copper. Okay? If another chemical has to bind as well, we call this a cofactor. So if you have to have phosphate plus vitamin B12 or plus copper or plus magnesium, the copper or the magnesium is a cofactor. Not a lot of enzymes need it, but there are a few in the body that have to have a cofactor. Now the ability of this enzyme to draw in, kind of like a magnetic thing, to draw in certain chemicals into the pocket, we call this affinity. So we're able to attract or to draw in certain chemicals. This is an affinity. Now officially, this little pocket here that we've labeled A, this is actually called an active site. So we have active site A, we have active site B. And any chemical that the active site draws in or has an affinity for, we call this a substrate. So active site A has an affinity for substrate F. Active site B has an affinity for substrate C. So we're going to pull these two chemicals in and add a phosphate, change the shape of the enzyme, and bring our two chemicals together to form a product. And then our enzyme will release this product. And then remember, we can reuse this enzyme, so it will then go back to its original shape and do the whole thing over again.